Hello, I'm Laura Marshall.
And I'm Melinda Rose, and this is Light Matters for October 10th, 2012.
On this week's show, quantum physics takes the Nobel. Nanoparticles help photodynamic therapy penetrate more deeply. The solar efficiency of black silicon is doubled. The European Space Agency wants to add a new dimension to its future cameras, and a physicist receives a Genius Grant.
Two physicists who demonstrated the direct observation of individual quantum systems without destroying them, something once thought unachievable, were recognized Tuesday with the 2012 Nobel Prize in Physics. David Wineland of the National Institute of Standards and Technology and the University of Colorado Boulder and Serge Haroche of the Collège de France and ENS in Paris will split the $1.2 million prize from the Royal Swedish Academy of Sciences. Working in quantum optics, Haroche and Wineland independently invented methods that paved the way for building quantum computers, which the Academy said has the potential to impact society in a way similar to how personal computers did in the last century. Wineland uses lasers to cool ions to absolute zero, which allows the measurement and study of individual atoms without disturbing their sensitive quantum states. Haroche is known for his work in quantum coherence. His experiments involve trapping photons between two mirrors in order to study their quantum state. His method allows observation of the photons just long enough before they decay, providing an important window into the understanding and controlling of particles. Wineland and his team also used ions in a trap to build an optical clock that is 100 times more precise than the microwave cesium-based atomic clocks currently used as the time standard. An optical clock is so precise that if you started measuring time at the Big Bang 14 billion years ago, it would only be off by about 5 seconds today. The pair will receive their award in Stockholm on December 10th.
Nanoparticles that convert near-infrared to ultraviolet or visible light could help overcome the skin penetration limits of conventional light-based therapy. Photodynamic therapy, or PDT, uses visible light, usually in the red wavelength, to activate a light-sensitive drug, but it's limited to a penetration depth of about 1 centimeter. Because of this limitation, PDT is currently used to treat certain types of cancer just under the skin and generally can't be used to treat large tumors or cancers that have spread. Near-infrared light, besides being non-toxic, is able to penetrate deeper into tissues. The new technique, developed at the National University of Singapore, manipulates gene expression by using nanoparticles to convert near IR to UV or visible light, and it could offer a safe, non-invasive therapy for deeper cancers. The researchers successfully controlled gene expression and hindered tumor growth in mice, and also were able to target the nanoparticles to specific locations. The team is working with the National Cancer Center Singapore to evaluate the technique's efficacy for clinical trials.
A solar material that takes advantage of a spectrum totally unused by standard cells could be the key to more efficient photovoltaics now that a team in Germany successfully doubled its efficiency. About a quarter of the sun's spectrum, the infrared, is lost in standard solar cells. Black silicon cells, however, are specifically designed to absorb nearly all of the sunlight that hits them, including the IR. Black silicon is produced by incorporating sulfur atoms with standard silicon and hitting it with a femtosecond laser. The method allows an increase in the number of electrons that can be created by a photon. Prototype cells have been built. The next step will be to try and merge them with commercial technology to increase the efficiency of standard cells from 17 to 18%. The Heinrich Hertz Institute team is also planning a spin-off to market the laser system to manufacturers.
The European Space Agency wants to add a third dimension to camera technology. It needs less resource-intensive systems than the conventional 2D cameras currently deployed on spacecraft and space rovers. Scientists at Thales Alenia Space of Belgium, Danish space sensor manufacturer Terma, and SINTEF, the independent research organization in Scandinavia, are conducting a study on behalf of the ESA to identify better imaging options for current and future space missions. Cameras are used in space for docking space stations, for navigating on foreign planets, and for safely landing spacecraft. 3D data is required in all these situations, but the cameras available are only 2D when used singly. 3D images are created by mounting several cameras together or by using complex computer calculations, which are unreliable and too power-hungry for regular space use. The organizations are working together to map system requirements, evaluate their strengths and weaknesses, and build a prototype for the ESA.
University of Arizona astronomer and optical physicist Olivier Guillon, who developed a breakthrough imaging technique for finding Earth-like planets outside our solar system, is a 2012 Fellow of the John D. and Catherine T. MacArthur Foundation. Guillon develops telescopes and other instruments to help find extrasolar planets, or exoplanets that, like Earth, orbit a home star. Such planets appear to orbit extremely close to their stars, but are much less bright, so they are hard to see. To overcome this, Guillaume invented the breakthrough technique of phase-induced amplitude apodization, which allows the use of a telescope much smaller than previously thought to work. Like the other 23 fellows, Guillaume will receive $500,000 in no-strings-attached support over the next 5 years. Here he explains how he hopes to use his award to involve the public in his research.
One particular direction that I think the fellowship is going to, I hope, help me push is involving the public and amateur astronomers in the search and discovery of exoplanets. And in the last 2 years, I've been working on how to make this technique affordable, easy for amateur astronomers, schools, and the general public to actually implement in their backyard. And so I'm really hoping that in the next few years, I can help others to actually use this technique to discover planets, and hopefully to engage the public and amateur astronomers into actual scientific research.
Guillaume is also an associate member of the Graduate Studies faculty at the University of Victoria in British Columbia and is a project scientist at the Subaru Telescope in Hawaii.
Sounds like he's going to make space study a lot more accessible for all of us.
Yes, let's all become citizen astronomers.
Let's. I'm especially excited about space news these days. We're just wrapping up the November issue of Photonics Spectra, which has a space theme. We're going to have feature articles on polishing telescope optics, the problem of image storage, and also lasers in space. If you're not currently a subscriber, you can sign up at photonicspectra.com. Look for the November issue the first week of November.
Well, that's it for this edition of Light Matters, Photonics Media's weekly newscast. We'd like to hear from you. Tell us what you like or don't like about our program. You can send your comments or suggestions to lightmatters@photonics.com.
You'll find links to share and subscribe to Light Matters by clicking the Share with Friends button on our video player.
Thanks for watching, and we'll see you next week.